I'm now very pleased to introduce Mike Brown, who's professor of planetary astronomy here at Caltech. Mike is famous as the discoverer of Eris, which launched a whole discussion of a whole new class of objects which are now not only important for us, but are possibly the islands that Freeman talked about. He's also the co-discoverer. I call him the co-discoverer of Pluto because somebody discovered Pluto as a planet, and he discovered it was not a planet. So he's responsible for that. So with that, I'm very pleased to introduce Mike, who's going to talk about the Kuiper Belt objects.
So I'm a little sad that I didn't get the Mike Brown needs no introduction, but there was a chance. So in preparation for our discussions of these icy bodies in the outer solar system, I asked Michelle to turn the temperature down by about 10 degrees. Is it working? Is everybody? Yeah. So I hope it's working out okay for you. So I'm gonna assume that many of you, most of you in the audience, are more sort of interstellar medium kind of people. And don't know as much about the Kuiper Belt, or that you're something else and don't know as much about the Kuiper Belt. So I'm just going to give you a general introduction to what's out there, what we know, and at the end, some of the stuff that we'd like to know. The title that was on the slide said the Oort cloud. I'm not going to talk very much about the Oort cloud because frankly, we don't know very much about the Oort cloud, but I'll talk about the stuff that's interesting is actually right here in this line that you're not seeing, which is between the Kuiper Belt and the Oort cloud. There is where we'll actually end the talk. So just as a quick reminder of the geometry out there, there's the Sun, Jupiter, Saturn, Uranus, Neptune, all out to scale. I don't know why I get this little thing. And as for a long time, actually the real scale, that's how big the Sun really is, and it actually is that shape. Nobody knew that. And for a long time, this was the only other object known out there. This is Pluto, which is right here right now. And it, as you can see, just kisses the orbit of Neptune at that point, goes a little bit inside. Always looked a little bit strange until the objects in the Kuiper Belt started being discovered. And at this point now, there are something like 1,500 known objects in the Kuiper Belt. And when we say Kuiper Belt, we generally mean these ones that are outside the orbit of Neptune. There are also this other population of objects inside the orbits of the giant planets. These are called the centaurs, and they're basically former Kuiper Belt objects that have perhaps had a close encounter with Neptune and gotten flung inside. These are the objects that are on their way to becoming short-period comets or on their way to being ejected. It just depends on whether they can make it past Jupiter, which is kind of the goalkeeper of the inner solar system. And if you look at the little blue dot right there, the little blue dot is Pluto again with its orbit that at the time it was discovered seemed crazy eccentric. And now you can see it does a pretty good job of defining both the inner and outer boundaries of the Kuiper Belt. And if you put all the other orbits of all the other Kuiper Belt objects on there, you would see a big mishmash of eccentric orbits and inclined orbits. Pluto's inclined by about 20 degrees. The other objects range from in the plane of the ecliptic up to 45 degrees. They're sort of all over the place, and it's very clear when you look at a plot like that Pluto belongs in this population of these excited small bodies in the outer solar system. Now, when they first people started talking about the existence of small bodies in the outer solar system, of small bodies beyond Neptune, it was because of this need for a population of this short period comets. And the initial ideas were that the Kuiper Belt would look something like this in now semi-major axis versus eccentricity spaces. You can look at it in a lot of different ways, but this is a nice way to look at it. It was thought that there would be, Neptune is here at 30 AU, and that Neptune would probably have cleared out the space in through here. Neptune would have excited a little bit of the edge right here, so you get a little bit of high eccentricities here. And as you move further out, and further out still, you get a colder, dynamically colder and colder disk. That's sort of the classical picture of what everybody expected the Kuiper Belt to look like. And so it was quite a surprise. One of the earliest big surprises is that the Kuiper Belt doesn't look like this. The Kuiper Belt looks like this. It's a much more interesting, much more dynamically excited. And even if you don't know anything about outer solar system dynamics or what's going on or how we classify these things, you immediately see, what is this giant finger here? What is this tail going off through here? There's a clump in through here, which you can't tell. There's a really small clump right where we originally thought things would be, but then there's a big excited clump. It's a diverse set of objects. We have names for all of them. We have reasons. These are things that this finger and this little finger here are both things that are at a semi-major axis where they're in a perfect resonance with the orbit of Neptune in the case of these objects called Plutinos, because Pluto is probably right there. These go around the sun twice for every 3 times that Neptune goes around the sun. These objects in the 2 to 1 go around once for every 2 Neptune orbits, and there are actually all these little objects sticking up in here are in other crazy resonances up to things like the 12 to 7 resonance. Neptune goes around 12 times, 1 goes around 7 times. Turns out the 12 to 7 resonance is freakishly important in the outer solar system. And then there's all the objects here. There's a change in scale right here at 50 AU, so I could extend it out. So there's nothing actually crazy going on here. This solid line is the line where if you're above the solid line, you cross the orbit of Neptune. If you're below it, you don't cross the orbit of Neptune. And you can see there's a slew of objects in this almost Neptune crossing eccentric but very eccentric orbits. And these are ones that have, again, had a close encounter with Neptune or a series of close encounters with Neptune, gotten flung outward, and then their orbits slowly migrated out just a little bit so they no longer cross Neptune's orbit. And they're not totally stable, but they're okay for longish periods of time. These guys that cross Neptune, they're in bad shape. If the ones here are okay because they're in the resonance that protects them from encounters with Neptune. Pluto comes closer to Uranus than it does to Neptune. So these guys are okay, but these guys won't exist for very long. So they'll have rapid dynamical evolution. These will be the ones that either become the closer in centaurs or they just get ejected or something interesting happens to them. So one of the biggest questions for early on is where do you get this crazy and dynamically very excited population of objects out here in the outer solar system? And you can't do it just from, the biggest thing that's out there is Neptune sitting right here. And basically the objects from, at least from 40 AU outward, if not a little bit closer in, just never come close enough to Neptune to really have been affected by Neptune in the at least recent history of the solar system. Early on, this led to the very early ideas that Neptune, and in fact all the giant planets, had migrated. It was a pretty exciting moment when it was kind of the same time that the first hot Jupiter exoplanets were discovered, and everybody started talking about migration there. And I think the switch flipped too in the solar system, and everybody realized that all of these signatures in the outer solar system, you could really only explain if the giant planets had moved around too. People had sort of thought about that a decade earlier and kind of had it in the back of their head, but nobody really took it very seriously, I think, until both the Kuiper Belt and the exoplanets at about the same time. The original idea was that the planets had all smoothly migrated outward. As they smoothly migrate outward, if you get an object into, say, the 3 to 2 resonance right here, when Neptune's over here, the resonance is here. As Neptune migrates outward, it actually traps it into the resonance, and it also increases the eccentricity. So as you move outward, you increase the eccentricities into things like that, and you capture the 2 to 1. These are all things that are scattering by Neptune and actually driving that migration. For about a decade, this was the sort of going theory of how the whole solar system had evolved, and there were many nagging problems with it that didn't quite work. And these nagging problems have all been solved with an idea that I think is very compelling. It's one that most people who work in the solar system are fairly convinced something like this happened, although there are some big... there are a lot of people who don't like it because they want their own idea to work, I think. And so here's the idea. If we look at now Jupiter and Saturn, which are the big dominant drivers in the outer solar system, Jupiter at 5.2 AU, Saturn at 9.2 AU, they are close to being in a resonance. They're close to this 2 to 1 resonance. Jupiter and Saturn are 1 AU away from being resonant. And even the fact that they're in that close resonance drives a lot of the eccentricities and inclination evolution of the solar system and makes things much more excited than they would be. But they're not in a resonance, so that's good. But remember, I told you that the ideas were that all these planets have evolved, dynamically evolved, and that evolution would have taken the early Saturn, Uranus, and Neptune, moved them outward, and Jupiter, the early Jupiter, moving inward. So if you run back in time, you could end up with a situation where you're sort of like this. Jupiter is in fact a little bit further out now at 5.6 AU. Saturn is further in at 8.6, and notice now Saturn is inside of the 2-to-1 resonance. If Saturn started out inside the 2-to-1 resonance and slowly evolved outward by basically scattering Kuiper Belt objects outward, as Saturn evolves outward, eventually hits that 2-to-1 resonance. If you put Jupiter and Saturn into a 2-to-1 resonance, you're basically taking the two most massive objects in the solar system and shaking them really hard and watching what happens to everything else that goes with them. And it's a mess. Let me show you the mess. Here's a simulation of, here's Jupiter, Saturn, interestingly, Neptune and Uranus, not Uranus and Neptune. And you can see they're packed in much more tightly. So here's Jupiter's at 5. Saturn will eventually end up here at 9. Uranus will eventually end up at 20. Neptune will eventually end up at 30. So the Kuiper Belt, this is the Kuiper Belt, and the planets are much more compact than they start with. And again, this is semi-major axis versus eccentricity. And you see that there's just basically a blob of objects out here, but you get this tail of high eccentricity, higher semi-major axis objects. These are the objects that are interacting with this planet right here. They get scattered outward, and they are the things that are actually driving the migration. I'm going to step through this a few frames at a time. Nothing happens for a long time because that evolution is really slow. So I've gone up to, this is 320 million years after the beginning of the solar system, and they start to evolve. They've just hit the 2-to-1 resonance, which suddenly starts to drive Saturn's eccentricity up a little bit. And critically watch these two guys. As these two start to go higher eccentricity and they start to oscillate back and forth, suddenly these two planets start to get eccentric. And this is bad news. If this guy gets just a little bit more eccentric than he is right now, he's going to cross Saturn or even Jupiter's orbit. You can imagine that's not a nice thing to do if you're Uranus or Neptune. And just about now, the inner one has crossed the orbit here, has been tossed outward, and when they toss outward and they get, that's a bad place to be. And it's bad for not just them, but for the entire Kuiper Belt, which explodes. And that explosion dynamically excites everything. All this, yeah, it's all gone then. And it removes about 99.9% of the material in the outer solar system. So what we have left is just a remnant. So I'm going to show you now. I walked you through the critical part slowly, but let me just show you the movie because you see it and it just goes all gone. These objects eventually, by scattering these objects away through dynamical friction, they get down to lower eccentricities, and they will eventually do that little bit of migration outward. But what it leads to is you can use this idea. It explains a lot of different things that have happened in the solar system, so it's very compelling in many ways. But it can lead to a large population of objects here. In this resonance, a large population in the 2-to-1 leads to a little bit of a classical. We call this classical because it's the thing that everybody thought they were looking for when they started looking. So it's a very compelling idea on why the structure of the Kuiper Belt looks like it is. So let me remind you the distances here. There is this edge to the Kuiper Belt that nobody quite understands here at around 48 AU, the clump of objects in the Kuiper Belt, and the actual number density in space of objects in the Kuiper Belt really drops off dramatically at 48 AU. But there is this very big tail of objects that have semi-major axes. I cut it off here. There are objects that have semi-major axes of 1,000 AU and eccentricities of whatever they need to begin seeing. All these things are discovered, of course, when they're down here at perihelion. We don't see them very well. It's that 1/r⁴ that you just heard about, which is a big problem. So in the context of what we've been talking about today, here's 100 AU. A lot of the Kuiper Belt is inside here, but we have, I always like to say, we actually have a lot of interstellar probes right now. We have objects that spend most of their time out here at 10 to the third, even further out there, that are their surfaces are being processed by whatever the environment is in the interstellar medium, and then they come back in and we get to look at them and see what they're like. So far, we've not been able to tease out any differences in what the Kuiper Belt objects that are those distant ones, the way they look versus the ones that are close. But we're getting better at being able to find these ones that are further away. And so I'm intrigued to see if we can eventually find something out there like that. The other interesting context is the size of the Kuiper Belt objects. This is the plot that you never get to see, which is the planets in their actual sizes. Usually you see like the kids' lunchbox where all the planets are the same size, and Pluto is the same size, and everybody says, "Why isn't it a planet?" Well, it's because it's one of these. You know, it's really tiny. But if you put them all in context, these are the asteroids in their actual sizes series, and then 10 asteroids are big enough to appear as one PowerPoint pixel. That's the criterion. And many Kuiper Belt objects. The Kuiper Belt is significantly more massive than the asteroid belt. In fact, the difference between Pluto and Eris is about 25% more massive than Pluto, and that 25% more massive than Pluto is the entire mass of the asteroid belt. So that's how much more massive it is out there. So there are a lot of big objects, big by sort of Eris and down-sized objects, and they have been the ones that we've studied the most. So if we ask ourselves what these things are like, we actually, just like has happened with Pluto for 20, 30 years, each one of these has now been studied in sort of gory detail and each one of these tells an interesting little story about what's going on in the outer part of the solar system, which is each one of these has fascinating stories. There's huge collisions and slabs of methane that you could ice skate on, and I'll talk about this guy, and icy eruptions, and it's a really interesting area out there to talk about. And I'm going to just give you the quick overview of what we know as a function of size. The biggest objects, the biggest bifurcation out there is between the largest objects. This is, I don't know how to get rid of that little slide down there. How do we get rid of you? I don't know how to do that. I don't know. Well, you have this says diameter, and this says kilometers. And so if you look at the size of the object here versus, let's just call it temperature of the object, you see this nice bifurcation where a small number of the largest objects, Sedna, Eris, Pluto, Triton, Maki, Haumea, Quarwar, a small number of these are big enough and or cold enough to keep their atmospheres. Basically, they have frosty surfaces, so they have methane and CO and N2 on their surfaces and in their atmospheres, and they acquire this rich phenomenology of atmospheric and surface processes that are interesting to study. The vast majority of them are too small. They lose all their volatiles right away, and instead of having interesting atmospheres and frosts, they have interesting irradiation processes. They have organics on their surface that you can try to understand. They have, if you look at the big objects that we talked about, so this is absolute magnitude this is planetary scientist absolute magnitude, which is even stupider than astronomers' absolute magnitude. But just think of it in terms of size. This is small, 25-kilometer-ish objects. These are 1,000-kilometer-ish objects. So the big ones that I was talking about that had the frosts, they're all over here. And if you look at the things just smaller, so the nice thing about getting rid of the frosts is the frosts, although they're interesting, they cover up whatever else is going on there geologically. And if you look at the ones with no frosts, the very biggest ones with no frosts instead have these huge amounts of water ice on their surfaces. It's not surprising these things are mostly rock and ice out there, but actually the fact that the biggest ones have the most water ice, and they shouldn't. All these things should have been processed enough that pristine water ices should have been covered up by organic goo early on. The biggest ones clearly have evidence that they had basically icy cryovolcanism Not currently. I don't think that that Charon or Quaoar or Orcus have these big icy volcanoes going on now, but they clearly have these vast plains, these magma plains where magma is ice, pure ice on the surface of these guys. You get down to about 500 kilometers, which is where you are here, and you start to just see some ice, some not ice, some ice, some not ice. And you're seeing basically, these are the small, undifferentiated objects, collisions, and organics that are dominating all these in through here. When you get down to even smaller sizes, where we can't see them in the Kuiper Belt, you have the comets. The biggest comets we know are 10 and 20 kilometers. Most of them are a kilometer, and that's the range in here. So then you can, if you take one of these guys and bring it into the inner solar system and watch the gases evolve off of it, you can learn a lot more about it. Everything I've talked about right here has been what we can have learned about the outer parts of the objects. And the outer part of the objects are interesting, but the surfaces are just a tiny, tiny fraction of what's inside. And what's really the fundamental thing that we would like to know about what these things are made out of is, and I said they're made out of ice and rock, and the question is how much ice and how much rock. A decade ago, we knew the answer perfectly because we had one measurement, and it was Pluto. And Pluto had a density that it was something like 2.00000 grams per centimeter cubed. And when everybody predicted what everything else would be in the outer solar system, the answer was 2.00000 grams per centimeter cubed. And in fact, the models for the chemistry of the outer solar system, the chemistry of the solar system itself, were all constrained by the fact that everything in the outer solar system had to be 2.0000. And we now have measured the densities of enough objects in the Kuiper Belt to know that this is significantly more interesting. To measure the density, you need a mass. We can only get masses of objects with satellites so far. And you need to know the size. So sizes are measured, thermal measurements from Spitzer and Herschel, sometimes occultations, sometimes direct measurements from HST. And you get this crazy plot that I'd like to show you, which is here you can see, diameter again down here versus the density in grams per cc. Here's that 2.00000. Pluto's actually gone down as it's, so it's no longer even itself. There are big things that are close in density to 3. 3 is a rock. Silicate rock is about 3, ice is about 1. So you're basically just looking at the ice to rock ratio. These smallest objects are under 1. They are lower density than ice. So they are presumably mostly just water ice, but also with a lot of porosity. And the one that just blows my mind is here's a 700-kilometer Kuiper Belt object with a density of about 0.7. So even there's very little porosity that you can stick inside of a 700-kilometer Kuiper Belt object. The smallest ones are basically ice cubes with very little rock. But the biggest ones are basically rock with a little bit of ice. And in between, it's sort of in between. And that is, you look at that and people say, OK, that's kind of weird. But it's actually not just kind of weird. It's really weird. Here's why it's really weird. You build these things, at least theoretically, you build these things by building up a bunch of these things. It is very difficult to take things that have no rock in them, put them together, and suddenly make rock. I've tried. It just doesn't work. And so understanding how to build these things out of these things, or build these things without building them out of these things, is an interesting thing going on in the outer solar system right now. And that's my favorite picture of what's really going on, is that if you say rock to ice ratio and draw pictures, small ones are all ice, big ones are all, a lot of them are kind of rocky. One of them is almost all rock. Pluto and Eris are about the same size, but very different in rock to ice ratio. In fact, Eris is more like Triton, but with some of its ice removed. It has the same sort of rocky core as Triton does. It's a crazy place out there. Let me end by telling you that interesting area in the middle between the Kuiper Belt and the Oort cloud. I'm going to show you one object that we discovered almost a decade ago now. Here was the Kuiper Belt that we knew then. Here was the object that we discovered. And we were pretty excited when we found something this far away because we thought maybe it's going to be in a circular orbit, kind of like you would think a planet would do. But we knew it might actually just come in like this, like a lot of the Kuiper Belt objects do. And so we got a series of more observations, figured out where it was. And the answer is it's none of the above. It does this. Yeah, that's what we said. So the closest approach to the Earth, this is Sedna. The closest approach to the Earth is 76 AU. Happens on September 23rd, 2076. Having a party, you're all invited. It goes out to 1200 AU. The aphelion is a little harder to know, but it goes out to something like 1200 AU. And I'm going to, since I'm yellow, I'm going to skip the interesting part about how it got there and why, although I'll do it very quickly. I think the answer to how it got there and why is that it's basically the early inner Oort cloud. If it went out to 100,000 AU, it would not be surprising. It's just the Oort cloud. It's actually the fact that it doesn't go very far. It's too far away from the planets. It's also too far away from the stars and the galactic tides. It's in this weird no man's land in the middle. How do you get in the weird no man's land? I think the answer very quickly is, here's a process like this. You start out as a normal Kuiper Belt object. You have a stellar encounter early on. It changes your orbit, and now you're stuck forever. Problem is, you shouldn't have these stellar encounters unless you are in a much more dense stellar environment than you are now, like a cluster. So what I really think is that this is the signature of early formation in a cluster. And in fact, this is about the right cluster. This is a NGC 7129. This is a little too dense. Actually, right about here is a good spot for us to have formed in a cluster with that sort of density, would have led to these things. So we're looking for more of these things for that reason. But the other interesting thing that I want to, that's obvious, once you find one of these things, you realize we could have only detected it for, I have 0 time left. We could only have detected it for 1 part in 60 of its orbit. So chances are that means there are a lot of these things out there. And if you, based on our surveys that we've been doing over the past decade, a couple of more discoveries, the population in that inner Oort cloud is something like 30 or 40 times the mass of the Kuiper Belt. And you can imagine, we know that the biggest objects in the Kuiper Belt have masses of things like Eris and Pluto. The biggest object in this population, you can extrapolate. Extrapolation is always dangerous, but if you extrapolate, the biggest object is something like the mass of Mars, or perhaps the mass of the Earth in this region out to maybe 1,000 AU, which gives you a population out there. You know, here's the Kuiper Belt, all very well and good, but here's where all the action is, out in this region here. As you just sort of heard this in the last talk, there's Mars. I know that's the size of Mars because I cut and pasted it from up here and brought it down there. So this is out to 1,000 AU. 6,000 AU would be even better, but even finding just these objects out through here, or finding, and then if we're talking interstellar probes, I think of more like finding them first, and then since we are sending them in all different directions, sending by some of these things that we discover out there. We're in the early stages of discussion right now of building a dedicated telescope to search for these things in the very outer part of the solar system. It would be installed at a secure, undisclosed location in the Middle East. And it's true, a little odd, but true. We'll see if that really comes to fruition. But that's where I think the interesting part of the science is going to be over the next decade, and we're excited to really start to explore this new region out through there. Thanks.